Our first speaker of the afternoon is Nick Weininger from Google, who will be talking to us about monotonicity in the Ising model.
Let's see, let's fit this to the screen. So yes, so the Ising model, Raisa, I believe, in the morning mentioned it briefly as one of a class of models whose study in the computer science and statistical mechanics fields has become common. And unlike some of the other models she mentioned, it's not at least necessarily an inherently iterative thing. It doesn't have to evolve in time. In its simplest form, it's just a probability distribution on the set of vertices, a set of configurations or spin configurations of vertices of a certain graph. And if you're a statistical mechanics type person, the way you deal with it, the way you prove the things you're interested in about it, is to look at it on finite graphs and then try to take some sort of thermodynamic limit as the graphs, for example, lattices in some number of dimensions gets larger and larger. But I like the Ising model purely as a combinatorial object. I think it's worthy of study in its own right, in the sense that you can make some very natural and simple conjectures about it, that when you look at them, you say, oh my gosh, that absolutely must be true. And then when you go to try and prove them, it turns out to be quite a challenge. So I'm going to talk about a couple of those. So the Ising model, as I say, is a probability distribution on spin configurations of a graph. And a spin configuration is just an assignment of plus and minus ones to the vertices. If you are a statistical mechanics person, you think of these vertices as particles of, say, atoms of some metal embedded in a lattice, and their spins as magnetic spins up and down, and they have magnetic interactions between them, and they may have some external magnetic field imposed upon them. And so the probability distribution's definition encodes that. You specify it by giving the weight of a typical configuration sigma in terms of these pair interactions j sub xy and the external fields h sub x. If, for example, for a given edge in the graph x comma y, you have a positive value of jxy, that means that whenever sigma x and sigma y, the spins at x and y are the same, so their product is 1, you get a bonus. The probability distribution prefers such configurations. And likewise, if you have a positive h sub x at a given vertex x, that's a field that causes the probability distribution to be weighted more heavily toward configurations in which sigma x is 1. And if all these weights are positive, the configuration, the model is called ferromagnetic. Again, from the physics folks who say, these are the models you actually want to use to study ferromagnetism. This one other little terminology thing that's important, the normalization constant, which is just the sum of all these weights, of course, is called the partition function of the Ising model. And it's really, if you want to do any serious calculation or computation about Ising models, you end up working with partition functions. So a very simple example here. Let's see if I can, next slide. So just to give you the most trivial possible example that's not completely trivial, you have a graph on just two vertices with an edge between them, and the 3 and the 2 are the magnitudes of the external fields of the two vertices. The 1 is the pair interaction between them, and so you want the probability of this particular configuration. You say, okay, this is -1, so it gets e to the -3, +2, -1 because they're different. So that's an overall weight of e to the -2, and then you divide by the sum of the weights for all of the different possible configurations. So, okay, why is this interesting? Well, for one thing, you might want to study some correlation properties of it. It's a well-known fact that's of interest if you're a correlation theorist, that if you have ferromagnetic interactions, all positive external fields, all positive pair interactions, then the resultant measure has what's called positive association, which just means that if you consider that space, so the probability space you're working on is plus or minus 1 to the n. You look at that as a Boolean lattice with sort of the obvious partial order, more plus 1s is up. And then any two increasing events in that partial order are actually positively correlated in the probability distribution. So, all right. So in particular, that means the following. If you have a ferromagnetic Ising measure, let's say it has 0 external field to simplify things, and you take 2 vertices v and w, then the event that sigma v, the spin at v, is 1, and the event that sigma w, the spin at w, is 1. These are both increasing events, and so they are, in fact, positively correlated. The expected value of the product of the spins is greater than or equal to the product of the expected values. So how strong is this correlation? Well, an obvious measure of that strength would be just the influence of v on w, which is, okay, you take the expected value of sigma w given that sigma v equals 1 and subtract the expected value given that sigma v is minus 1. And so you get, intuitively, what you get then is a measure of how much flipping the spin at v is expected to change the spin at w, how strongly the spin at v can influence the spin at w. And you might generalize this notion of influence by saying, okay, if we fix the spins of some of the other vertices, if we perform a conditioning on a certain subset of the vertices A to say we're going to fix some configuration of plus and minus 1s for just those vertices, and then reconsider the influence that V then has on W, what should happen? Well, again, intuitively, the influence should go down. The more you fix configurations of intermediate vertices between V and W, the less strongly V should still be able to influence W. Because again, if we go back a few slides, look at the definition. The Ising models, the influence just works through the pair interactions of adjacent vertices. The spin at V influences the spin at W because the spin at V influences the spin at its neighbors, which in turn influences the spin at their neighbors, and so on. And if you fix some of those neighbors, or some of the, more generally, the intermediate vertices spins, then whatever influence you had ought to be lessened. And that is the conjecture. The conjecture is due to Claire Kenyon, Elhanan Mossel, and Yuval Paris, and will be referred to hereafter as the KMP conjecture. And this is all it says, that for any set of intermediate vertices you take in any underlying graph, no matter how you set the boundary condition, for any V and W, you decrease the influence of V on W in the Ising measure when you set that boundary condition. So, a simple question. How far can we get on it? So K, M, and P in the paper where they stated this conjecture proved it in the case where the underlying graph is a tree. And this is but theirs is a technique that relies pretty heavily on the tree structure of the graph. If it happens that you want to just restrict the spin of a single intermediate vertex, then it's not so hard to prove. But even then, it's not trivial. It follows from a fact about Ising models called the GKS inequality. And what I managed to do is to prove it in the case where you have an arbitrary underlying graph, an arbitrary number of vertices, but where you restrict the boundary condition to be either all plus ones or all minus ones. And also in some very strange, fairly small cases where after you're done restricting your intermediate vertices in A, you only have a few left in your graph. So, okay.
Why can't you just fix one vertex at a time using one vertex result? Can you repeat the question? Isn't it still an Ising model after you fix?
So the question, okay, no, it's a good question. The question is, why couldn't you prove it simply by fixing one vertex at a time? And the answer is that a lot of the ferromagnetism conditions that you need to hold just don't any longer hold after you've set a couple of vertices. I mean, in any Ising model, you're right. You can look at a model with a couple of vertices fixed as another kind of model with different sorts of interactions and external fields on the smaller graph. The problem is that once you try and fix a second vertex, especially if you fix the two vertices in different ways, then some of your external fields end up being positive and some of them end up being negative, and all sorts of basic properties that you get to use when you have all ferromagnetic interactions just go out the window and are no longer true. So yes, that's why it's not quite that easy. But in the case where you have all plus ones or all minus ones, what you can do is use a very interesting sort of method that seems to work unreasonably well for these particular sorts of models, called the duplicate variables method. And so again, you have these partition functions. And it turns out that when working with Ising models, you can rewrite just about any problem, any inequality you want to try and prove as an inequality that involves partition functions alone. And by a series of reductions to doing that, you get that, okay, the inequality you want to prove now becomes an inequality with a product of 4 partition functions on each side. So this looks like a really messy thing to deal with, but we're going to make it a slightly less messy thing by going as follows. So we're going to group the 4 partition functions on each side into 2 groups of 2, and we're going to think of each product, and this is where I should... So a single partition function, remember, is just a sum of weights over possible spin configurations of graph. So product of 2 partition functions, in general, you write as, say, z1, z2. If you want to write it as a single sum, you write it as a sum over pairs of spin configurations, and you have a paired, some weight function, weight of sigma times a weight of tau. And then the thing you do is you just regroup this summation as a summation over a sum, as a summation just over subsets of your original vertex set. And say k of s. And the way you do this is you simply collect into one summand all those summands over here where the 2 underlying spin configurations agree precisely on S and disagree precisely on S complement. And so the reason why this is at all useful, the reason why you would ever want to do this, is just that, again, we're dealing with pair interactions in external fields only, and if, let's say, you have a configuration sigma, which is plus here and minus here and minus here, and a configuration tau, which is, let's say, plus here and minus here and plus here. So this is your S, and this is your S bar. These weights, sigma and tau, are determined in the zero external field case only by the pair interactions. And if you have the pair interaction between a vertex here where they agree and a vertex here where they disagree, then no matter what you do, no matter how you set the agreeing spins of these vertices or the disagreeing spins of these vertices, you'll get opposite signs for the product of these 2 and the product of these 2. And so the weights, the contributions to the weights there will cancel out. And so you get a partition function. What this summand turns out to be is a partition function for an Ising model that is now restricted only to S times a partition function for another Ising model that is restricted only to S bar. And the usefulness of that is that if you now have a nice pair of sums on each side where they're sums over subsets of your original vertex set, then you might hope to conclude that your inequality is true using this wonderful tool called the Alswede-Dakin 4 functions theorem, which says that if you want a thing like this to be true, it is sufficient to show that these summands satisfy a certain local submodularity condition. And indeed, that's how you go about doing this KMP inequality in the all pluses case, is You just reduce that using this process, and you show that the local submodularity condition is in fact satisfied. But the duplicate variables thing, again, is sort of a key and cool method. So let's see. All right. Now, the second of these conjectures. How am I doing for time? Okay, pretty well. The second of these conjectures involves what you get when you do try to convert this Ising measure into an iterative model, into something that evolves over time. So we want to make out of this static probability measure a Markov chain that converges to it, that has this static Ising measure as its stationary distribution. And a very simple way to do it is by defining the steps that might call heat bath steps, where at a given time step in our iterative process, what we're going to do is pick a vertex in our graph. So we've started at time 0 with some fixed spin configuration. We want to evolve toward the Ising model as the stationary distribution. So we pick some vertex in the graph. We fix the spins of all the other vertices, and we just pick a new spin at x according to the appropriate conditional Ising measure. So essentially, we erase the spin at x and reset it in a random way, again, according to the Ising measure we want to converge to. And iterating this process gives you what is called the glabra dynamics. And the glabra dynamics just says, well, do this at each time step, and you get a Markov chain. If you do it, and you can do it with random choices of vertices, or you get or you can even fix the sequence of vertices you choose deterministically. And again, okay, we get a natural monotonicity property that we would like to be true out of this. If we have a ferromagnetic Ising measure, then in that Ising measure, the more we strengthen the external fields and the more we strengthen the pair interactions, the higher the expected spin in that Ising measure of any given vertex. So if it's true at the stationary distribution, and we have this Markov chain that converges to the stationary distribution, we might naturally ask, okay, is it true at every step of the way? Well, it's clearly not true if you don't start with the highest possible configuration as the starting point of your Markov chain. That's fairly easy to see. If you start with an all ones configuration, if you start with an all minus ones configuration, for example, and iterate this process, then the stronger the pair interactions are, the more likely it is that you will remain in all minus ones, and so the lower the expected spin of your initial vertex. But conversely, if you start at all plus ones, you should have more likelihood of staying at plus one at any given vertex. The stronger you make the pair interactions, the stronger you make these preferences for adjacent vertices to have the same spin. And so, again, that is the conjecture. The conjecture is due to Paris. And it turns out to be quite difficult to prove, even in what you would think are fairly trivial cases. So here is what you might think is a trivial case. And so, for example, we can think of just doing a two-step process that in some sense approximates it. We can specify a given vertex x and rather than fixing the configuration of all other vertices, we can choose a random configuration of all other vertices according to our stationary measure, now conditioned only on the fixed spin at x. We can do that in step 1, and then in step 2 choose a random spin for x. And so in some sense what we've done is run the glabra dynamics to infinity on all of these vertices, fired all of these vertices again and again. And then at time infinity plus 1, here we are picking the spin at x, and we want to know that after that one firing of x, we get monotonic behavior of the probability that the spin is 1. So I managed to prove this. And the proof, again, is a duplicate variable sort of method. you want to show that the ratio of probability of 1 to probability of -1 is increasing in a given parameter. You can rewrite this as this product of two probabilities should be greater than that product of two probabilities. You rewrite that, again, using sort of standard Ising model reduction techniques as a product of these two partition functions should be greater than or equal to the product of those two partition functions. And then you do a duplicate variables rewriting, which again makes each of those products into a single summation over subsets of the vertex set. And it turns out that if you do that, then you can show that that every summand here is greater than its corresponding summand there. But it's only the particular method of putting things into bins that duplicate variables give you that seems to allow you to do that. And again, this is only a very simple case. So this is an unreasonably effective method. It probably points to some much deeper property of the Ising model. I've only really been able to scratch the surface of it. But I hope this demonstrates that at least there are some interesting problems that arise from the purely combinatorial consideration of the model. And I think I'll stop there.
We have plenty of time for questions for our speaker. Yeah.
Can you say slightly more about why you can't just keep removing one? Could you elaborate even further on? Repeat the question.
Okay, so the question is the elaboration on why you can't simply do it by essentially by an induction, right? Where you restrict one vertex at a time. So again, I'm going to go back to a slide that I skipped over. So at the end of all of your reductions to partition functions, you basically get that if you want to show anything, at least by this general method of let's see if we can prove things by partition functions and duplicate variables, then you have to prove this lemma about a submodularity property of pairs of partition functions of Ising models where you have different external fields but the same pair interactions. And in order for that to go through, you need to make the assumption that of these two external fields, one is not only positive but bigger in absolute value than the other. And if you try to do an inductive proof where you're not restricting the setting of the boundary condition, where you're not saying I'm just going to set them all to +1 at once, then that assumption, when you get down to the point where you need to prove something like that, this assumption about your external fields that you've reduced to is no longer true. And in the absence of that assumption, that lemma just doesn't go through. I mean, there's easy, small counterexamples.
Other questions? Okay, then the next talk will be at 3:30. Let's thank the speaker again.